today's warm-up question that you see on my screen. It's something that you should be able to answer based on what you did yesterday in the PhET, which, by the way, if you have not yet turned in yesterday's assignment, please make sure that you get that turned in as soon as possible so that you don't get a 0. We are going to be taking notes today after we go over this warm-up over waves, which is going to cover some of the stuff that you saw in yesterday's PhET assignment, along with some new stuff that we're going to add to it. So if you took notes yesterday, you can take those out and you can add to those as we go through this stuff today. Today's warm-up question says, what is the wavelength of the wave pictured? And so this is the wave that we're looking at. And if I want to measure wavelength, typically we would start here and we would try to find one full wave cycle, but that's a little bit difficult to do at that position. Because that position is just kind of in the middle of the wave. Could we do it? Yes. Would it be hard to tell maybe where it's at? Maybe. Okay, so in order to make it easier, I'm going to recommend that you pick a point from equilibrium or from a crest or a trough. So a point like here at equilibrium, although this point I wouldn't choose either since it's not on one of my grid lines, or pick a crest or a trough. I picked a trough down here. And I did that because there's only one crest in this picture. So I'm going to use this trough, and then I'm going to, one full wavelength is going to be to the next trough. And so if I want to find the wavelength, I'm looking for the length of this wave, the horizontal distance from point 2 to point 8, which of course is 0.6. And so the wavelength of this wave is 0.6 centimeters. In this case, I measured it from trough to trough. But I could have measured it from equilibrium back to equilibrium again if those numbers had fallen at kind of a normal position. Or any point on the wave through one full wave cycle and back to that point again. That point, the first point was a little bit tricky to see, but you can tell that it would fall somewhere right around 0.6, but I can tell for sure when I use trough to trough. All right, so again, you should be able to do that because you had to measure wavelength yesterday in the simulation. Hopefully you were able to figure it out then, but if not, we're going to obviously go over it a little bit more today, including in this warm-up question. So let's go ahead and get to the notes with a few definitions, and then we'll get into kind of the meat of it. So a pulse is a single disturbance that moves through a transmission medium, and I have an image up here of a water droplet hitting the surface of the water. And you can see these wave pulses that propagate outward from that initial water droplet. And so you have these ripples through the water, but they're not regular repeating pattern of them. It's just kind of random. Whenever the water droplet falls, it sends out a couple of wave pulses. A periodic wave, on the other hand, is a wave with a repeating continuous pattern which determines its wavelength and frequency. And so you can see in the image at the bottom, this has a very regular pattern to its motion, to its oscillation, its shape, okay, all of that. And so that would be a periodic wave. So if you're jotting down definitions, pulse and periodic wave are both kind of new definitions. I know periodic wave may have been in the reading yesterday, but if not, write it down in your notes today. Okay, we also need to talk about simple harmonic motion, which is the repetitive movement back and forth or up and down, I should have added that, caused by a restoring force directed toward an equilibrium position. So all of these images show examples of simple harmonic motion, this repetitive motion of back and forth or up and down. If you focus on a single particle in this wave that you see here on the left, you can watch this red dot, and all it does is go repetitively back and forth and back and forth. And it does this as a wave is propagating across the screen. I can see the same thing here if I focus on this red dot. It's a repetitive up and down and up and down as this wave propagates across the screen. These other ones aren't really waves, but they do show simple harmonic motion, a repetitive back and forth motion of a pendulum, or this box on a spring, or either of these objects here, this red dot on this rotating disc, or this red dot on this spring. But all of these show this repetitive back and forth or up and down motion that's caused by some restoring force toward an equilibrium position. So when we view a periodic wave, Okay, those waves that have that regular pattern to them at the particle level, we can see that the particles undergo simple harmonic motion. These two images were the first two images on that last screen. And if you focus on one of those red dots, you can watch its regular back and forth motion, or its regular up and down motion. And what this tells us is that these particles aren't transferred by the wave. This red dot doesn't move across the wave from left to right through my medium. Instead, it just simply oscillates up and down, and as it does that, it transfers energy to the next particle, which transfers energy to the next particle, and it's kind of like a domino effect. And so the particles themselves aren't transferred. Matter doesn't move through the wave. Rather, energy moves through the wave, and those particles of the matter in these two examples are, again, kind of setting off a domino effect of sorts, where the movement of one affects the next, affects the next, affects the next, due to shear forces or tension, or due to collisions between gas molecules or something like that. Okay, but again, simple harmonic motion means matter is not transferred by a wave, it just oscillates, only the energy is transferred. So there are two basic kinds of waves that we need to talk about. Electromagnetic and mechanical. This unit that we are starting, or that we started yesterday, is really focused on mechanical waves. We will have another unit after this where we focus more on electromagnetic waves. For right now, I'm just going to go over kind of the definitions for both and enough information so that you can compare and contrast them. But we're not really focused on electromagnetic waves yet. Okay, we just need to know the differences between the two. So mechanical waves are going to include water waves, sound waves, waves on ropes or springs, the wave that you saw in the string yesterday of the FET. All of those are going to be mechanical waves. And mechanical waves all require a medium to travel through. There have to be atoms. And those atoms are going to collide with the next atom and the next atom, or that atom that's moving up and down in the string is going to affect the next atom due to those forces between them, okay, friction or whatever it may be. So those are your mechanical waves. That's different than an electromagnetic wave, because an electromagnetic wave does not require a medium and can propagate in a vacuum. And what I mean by vacuum is through outer space. Like light can make its way from the sun to the earth, despite the fact that there aren't really atoms in between the two, because space is an empty void. Okay, in both cases, both of these types of waves, mechanical waves and electromagnetic waves, transfer energy, but neither of them transfers matter. The matter doesn't move across the screen like when we watch those red dots. It simply oscillates back and forth or up and down, but the energy does propagate as the wave propagates across the screen. So we're going to focus in a little bit more detail on each of these. So here's some notes about electromagnetic waves. These are vibrations of electric and magnetic fields propagating through space with electromagnetic or radiant energy or radiation. So when I say electric and magnetic fields, that's what this is showing here. You can see here oscillations of these fields. In this particular image, the red wave represents the magnetic field oscillations, and the blue wave represents the electric field. And you can see how these are oscillating as this wave propagates. We still have this same type of back and forth motion due to the changes of this field. For your electromagnetic waves, they do not require a physical medium. So again, they can travel through the empty void of space. They transmit radiation energy. They're going to have more energy if they have a higher frequency. They travel at the speed of light, which is 2.99 times 10 to the 8th meters per second, or 6.71 times 10 to the 8th miles per hour. So these electromagnetic waves do include visible light. I said they travel at the speed of light. Visible light is part of that spectrum. However, electromagnetic waves could be radio waves or microwaves or infrared radiation or visible light, ultraviolet light, X-rays, or gamma rays. All of those are going to fall along that electromagnetic spectrum, and all of those are going to be examples of electromagnetic waves, and they're all going to travel at the speed of light. Again, we're going to focus more on this stuff next unit, but I do want you to know some basics for this unit so that you are able to see the differences and similarities between the two wave types, because you will have questions about that type of thing. Okay, so that's your electromagnetic waves or electromagnetic radiation. Mechanical waves are vibrations of matter that transfer mechanical energy through a material medium. So you do have to have a physical medium. Okay, you can have air that transfers sound. You can have a slinky that you oscillate up and down to transfer a wave. Okay, whatever it may be, it could be water. But you have to have atoms, and those atoms are going to collide, and those atoms are going to have forces between them that pull or push on the next atom. And so that's why these waves require a physical medium. So that light can travel through space, but sound can't. Okay. Your mechanical waves are going to transmit whatever mechanical energy you put into them. So if you make a wave by just shaking at the end of a slinky or the end of a string up and down, they're going to transmit that energy through that string or through whatever that medium is to the other side. And assuming that we have perfect conditions where we don't have energy loss due to friction or air resistance or whatever else, then the total amount of input energy that you put in, that's how much you're going to get out at the end of that wave cycle. More energy is going to come from a larger amplitude. So if I use greater force as I'm shaking the end of a string up and down, I'm putting more energy into it, the waves that I make will be taller. Okay? Or with sound waves, I'm going to get more energy if I'm louder. And so we'll look more at that in a little bit. All mechanical waves are basically disturbances or variations that travel through a medium from point to point carrying energy. They will locally displace particles in the medium as they travel, causing them to move from their equilibrium position and then oscillate about that position. Again, either up and down or left and right, depending on what type of wave we're looking at. So here's that same oscillation I was talking about. We've already seen this a couple times now, but you'll notice that the energy does propagate as the wave travels across the screen from left to right, but the actual particle of the medium that's highlighted in red simply has this up and down oscillation, this regular, repetitive, simple harmonic motion. And so that's not actually moving with the wave. That's what it's referring to here. Those particles oscillate about equilibrium. So there are two different types of mechanical waves, and you need to be familiar with both of these. So if you're taking notes, you might want to write down transverse waves and longitudinal waves, and you can see them both in the animation here with these slinkies. But these are these vibrations of matter transfer mechanical energy. Both of them do that, but there are two different ways in which you can do it. And so let's focus on one at a time, starting with transverse waves. So a transverse wave is a wave in which particles of the medium move in a direction that is perpendicular to the direction that the wave moves. So this wave, if you watch this animation toward the bottom left, the wave is moving from left to right. However, the particles of the medium are oscillating up and down. Pick any one of those points. I picked that red one, and you can watch it. It just goes up and down. So its motion is perpendicular to the wave's direction of propagation. If you have something that's perpendicular, one of them's going up and down, the other one's going left or right, they're at a right angle, then that's going to be a transverse wave. Okay, and those transverse waves are going to have this basic shape to them, same shape that you see here. You're going to end up with these displacement from this equilibrium position, and at those points where you have maximum positive amplitude, those are called your crests, where it's the tallest in the positive direction. And then where it has a maximum negative amplitude, you're going to have your troughs, and they're in this the lowest points that this thing reaches. So you do need to be able to label the parts of a wave as well. So go ahead and sketch out a diagram and label some crests and some troughs in that diagram so that you have something to look back at. So here again is a transverse wave. You can see in this one, and you saw it in the last one too, but the direction of vibration is up and down along my screen, whereas the direction of wave propagation in this particular example is to the left. So again, we have that perpendicular direction where your wave propagation is perpendicular to the particle's oscillation. That's going to be what characterizes a transverse wave. A longitudinal wave, on the other hand, is a wave where the particles of the medium are displaced in a direction that is parallel to energy transport. So these particles that make up the medium move in the same direction, or at least parallel to, back and forth, as the energy of the wave. So if you look at this example of a slinky, there's a hand here at the end that kind of just sends a pulse. It just pushes on it and sends this compression through the slinky. And if you look at it, obviously the wave is traveling from left to right across my screen. You can watch it move. But the particles that make up the slinky are also oscillating left to right. And so the direction of particle motion is parallel to the direction of wave propagation, and that is what characterizes a longitudinal wave. This earthworm moves in a similar way to a longitudinal wave because you can see that he is physically moving across the screen from left to right, and as he does so, you can see these areas where he's stretched out, and then this compression that moves forward to carry him forward. So just like we can label crests and troughs on a transverse wave, we can also label the parts of a longitudinal wave. Those parts are called compressions and rarefactions. A compression is a point on a medium through which a longitudinal wave is traveling where you have maximum density, where things are compressed and they're close together. Okay, like in the slinky, where the slinky is close together. A rarefaction, on the other hand, is a point on the medium through which a longitudinal wave is traveling that has minimum density, so that's the portions that are the most stretched out. Okay, and so you can label parts of these waves in a similar way to labeling parts of your transverse wave. So again, here is an animation of a longitudinal wave in a slinky. You can see that he sends wave pulses in the slinky, and you can watch these compressions move or propagate to the left. And then you can also see the actual rings of the slinky moving, vibrating back and forth. So again, everything here is parallel. The direction of the wave is parallel to the direction of vibration. That's what's going to characterize your longitudinal waves. All right, so here I said I'm asking you to go ahead and draw these images on your paper. If you're taking notes, this would be helpful for you to have if you don't already have some pictures drawn. Draw the following images of waves A and B in the slinky. Label the longitudinal wave, and then label the wavelength for each wave. So make sure that you know how to label a wavelength. I'm going to go over it with you, but I want you guys to try it first. Okay, so take a look at the images here, draw them on your own paper, and then see if you can label a wavelength and determine which one's longitudinal. I'm going to give you 23 seconds to try that, and then we'll discuss. Have an answer ready in case I call on you. All right, so let's see. Skylar, which one is your longitudinal wave, A or B? B. Yeah, that wave B is going to be your longitudinal wave. Guys, what do we call wave A? The other one, yeah, transverse. Okay, so be able to identify them by picture like this. We have a transverse wave for A, a longitudinal wave for B. And then let's go ahead and label the wavelength. Okay, now we can label the wavelength of our transverse wave from crest to crest or trough to trough. We did trough to trough in the warm-up. That's also what I labeled here. But you could label it from crest to crest, or if you had an equilibrium position kind of labeled in here, and I don't, that would be another point that would be easy to measure from potentially if it was in there. So this is a wavelength. You could have also gone from this crest to this crest. But one full wave cycle is going to be from trough to trough or crest to crest or equilibrium, and then through a crest and a trough and back to equilibrium again, just like you did in the FET. However, you did not mess with these longitudinal waves in the FET, so you haven't really seen these as much. If you want to label a wavelength here, I'm going to recommend that you label it from compression to compression because that's the easiest point to see. It's kind of more difficult to see where the rarefactions are. You could label it from rarefaction to rarefaction. That is also correct. But I think because the compressions are so much easier to see, it's an easier point to measure from. But that would be your wavelength for this longitudinal wave from this compression to this compression, or pick any two subsequent compressions or rarefactions, and you can measure that. So again, my wavelength of my transverse wave I measured from trough to trough. The wavelength of my longitudinal wave I measured from compression to compression. All right, so here is a question that you will see again. It's going to show up in your assignment in MyOpenMath. It's also something that we have asked previously on quizzes and tests, so you might want to jot it down. It's also something students tend to miss. Okay, that's why I have it up here. But it says, a wave propagates to the right as shown. Which direction will the highlighted particle move in the next instant? Before you answer the question, this is a transverse wave. Okay, I know that this wave is going to move across my screen to the right, which means I know that the particles of the wave have to vibrate perpendicular to that, meaning they're going to move up and down. So my answer is either up or down. Don't put left or right. It's not going to do that. It's going to be up or down because that's the direction of the oscillation of the particles. It's got to be perpendicular to the wave's propagation. So the question is, will this move up or down in the next instant? What do we think? I just heard one person whisper. But it's going to be down. Okay, again, this is a common misconception because students want to think of the particle on a wave like a roller coaster car moving along a track, and that's not what happens. Instead, the wave moves through that point. And so I put the screenshot that we were looking at up here. So if we watch this, it's going to be right now is whenever it gets to that point. I'll wait till it does it again. Right now is when it's at that position. And the next instant, it's moving down. Okay, so whenever you have that crest right here, this is moving down. And it's because if you look at this image, this wave is going to be moving to the right. So this trough is going to end up over here. Okay, this crest is going to end up farther this way, so on and so forth. And so if this trough is ending up over here, that means this particle is on its way down so that it's at that lowest point in just a moment. The wave moves through the point. Okay, just like I lined it up perfectly there. But the wave moves to the right and passes through the particle. The particle does not climb the hill. Okay, that's not how this works. But it is a common misconception, and it is something you're going to see again, so you might want to jot it down so that you don't miss it. It is, if you want to look at this slide again later, which I'd recommend if you're not really following, it might be helpful to see it again. This is slide 20. All right, so again, you need to be able to compare and contrast not just electromagnetic waves and mechanical waves, but also the two types of mechanical waves, transverse and longitudinal. So I have some bullet points on my screen that you might want to copy down. Both a transverse and a longitudinal wave will transfer energy. Neither of them will transfer matter. Okay, again, you can watch the individual rings on these slinkies, and this ring only moves up and down. It does not move from left to right. Same thing here. This will oscillate a little bit, but it's not like the second ring of the slinky ends up over here at the end. That would be a really tangled slinky. And so neither of them is transferring matter, but they are transferring energy. Both require a medium to travel because they displace matter due to an initial force or pulse that transfers energy from one particle to the next, kind of like a domino effect. There is simple harmonic motion of particles in both of these. In our transverse wave on the top, my simple harmonic motion is that repetitive up and down motion. In the wave on the bottom, that longitudinal wave, I have the back and forth motion. If these slinkies were moving in a periodic wave, you would see that continuous movement. Here, it's really just single pulses going through. One other thing we haven't talked about yet, but it's at the bottom of my screen and you might want to write it down. Longitudinal waves are faster than transverse waves. In fact, if you watch these animations, you can see that this one reaches the end first before this one. Okay, and so your longitudinal waves are faster, and this is something that is evidenced if you've ever, I know y'all have learned about them, but if you remember learning about earthquakes, maybe in junior high or maybe you are taking earth and space science, those earthquakes, there are waves that propagate out from the epicenter where the earthquake occurs. And those waves are felt by people around the world at different distances, but they're felt at different times. There are two different types of waves. The P wave or pressure wave is a longitudinal wave, and that wave is felt first. The S wave is a secondary wave, that's the S, okay, and it is a transverse wave, and it arrives after that primary wave. So there's a vibration that is felt before the ground starts moving up and down. Okay, and so we see that in earthquakes as well, but longitudinal waves are faster than transverse waves. So here are a bunch of those terms that were in the reading yesterday. So hopefully you already have written these down. But when we start analyzing these waves, we can make and use following measurements, whether we're actually measuring something like in the PhET or just reading numbers and using them for calculations, which I'm going to show you at the end of the period today. But there are different variables that you need to know: wavelength, period, frequency, amplitude, and velocity. Wavelength is represented by the Greek letter lambda. It's the length of a wave. We did that one in our warm-up, and we typically measure it in meters unless the question tells you to do otherwise. Period is the time for one wave cycle to pass a point, and it is measured in seconds. It's the time for one wave. Frequency, on the other hand, is the number of wave cycles per second. So frequency and period are going to be inverses of each other, because period is time per cycle and frequency is cycles per time, cycles per second. The unit for frequency is thus hertz. It's not measured in seconds. It's technically cycles per second, or an inverse second, which is also a hertz. Amplitude is your maximum displacement of the medium from rest or equilibrium position. I'm going to go into that one a little bit more in depth later on in the notes. So we're going to revisit amplitude later on. And then velocity is distance traveled by a specific point on a wave, such as a crest, in a specific amount of time, and it will be measured in meters per second. Another common misconception that you might want to make note of is that wave frequency and wave velocity are not the same thing. Sometimes people hear, oh, this one has 3 cycles per second versus 1. That does not make the wave faster. In fact, if you look at my animation, I have a wave with a frequency of 3 hertz and a wave with a frequency of 1 hertz, and they have the same velocity. Okay, so frequency is not the same thing as velocity. If you watch this blue arrow, you can see that each of these waves has a crest that is traveling at the same speed, the same rate across the screen. Again, so do not mix the two up. Yes, the one on top has a greater frequency, but it is not moving faster. Okay, velocity depends on the medium. Because these two waves are traveling through the same medium, it's the same string, okay, this made of the same material with the same tension, all the variables are the same, then they're going to travel at the same velocity. Now, if you start changing the material of the string or the tension in the string, or it's not a string, it's now moving through some other type of material, then yeah, you're going to see differences in velocity because it depends on the medium through which the wave is traveling. All right, so let's see if we can practice doing applying a few of the things that we've been talking about. So this question says, identify the number of waves in each example. And I have 2 pictures, A and B, and if you want to sketch them on your paper, you can, but I'd like you guys to try and see if you can count how many waves are in each one. If you're not sure, talk to your neighbor. But I'm going to call on 2 people in just a minute, so have an answer ready. You guys have 32 seconds to discuss. It might be easier if you draw them out on your paper. Bless you. All right, so wave A. Carly, what did you ladies come up with? How many waves do you see there? What do you think? Yeah, 4. Okay, wave. There's 4 of them. You can draw it in. It's easier if you draw it in. Okay, but there's your wavelengths. 1, 2, 3, 4 wavelengths. Therefore, 4 waves. Okay, Dallas, what did you guys say back there for wave B?
2.5.
Perfect. 2.5. I gave you the tricky one. Okay, that one doesn't have a whole third wave, but it has more than 2. Okay, there's 1 wave, there's 2 waves, and then there's just the crest portion of the next one. That is 2.5 waves. You might have an image like one of these and be asked to do calculations, so it's going to be helpful if you can count the number of waves in those types of pictures. Same pictures. It says if each image occurs over 20 seconds, what is the period? for each sample. So again, look back at your definition for period if you don't remember, but see if you can figure it out or talk to your neighbor if you're not sure. You have 29 seconds to discuss, and again, I'm going to call on some people, so make sure you have an answer, especially if you haven't been called on yet. All right. Taylor, what did you ladies say for the first one? What's your period?
5.
Perfect. 5 seconds. Again, period is the time for each wave. So if you have 4 waves that take 20 seconds, the time for each one, 20 divided by 4, is 5 seconds. What about wave B? Axel, what did you guys say?
We got 8.
You got 8. You got the right answer. Okay, total time divided by the total number of waves. Okay, so 8 seconds because it's 20 divided by 2.5. Perfect. All right, the next one's frequency. Okay, frequency, guys, is inversely proportional to period. So we already found the period. We could just do 1 over 5 or 1 over 8 to get the answer. Alternatively, you could go back to the definition. Frequency is the number of wave cycles per unit time. So we already know how many waves there are. We can just divide it in the opposite order. So you could do this 1 over 5 or 4 over 20. Either way, you're going to get 0.2 hertz for the first image. For the second one, same thing. You could do 1 over 8 or 2.5 over 20, and you're going to get the same answer, 0.125 hertz. Okay, so be able to answer questions like these for different examples or different wave pictures. All right, I told you we were going to come back to amplitude. You probably already have at least a little blurb written down about amplitude, but you might want to add to it. I have the definition here. The maximum distance moved by a point on a wave measured from its equilibrium position. It is equal to 1/2 the length or height of the vibration path, the vibrational path. Now, you may or may not have that sentence written down, so you might want to add it, but you definitely want to add this last one. Energy is directly proportional to amplitude squared. Okay, so if I give you a question that says, hey, what if I double the amplitude of this wave? How does that affect energy? Or what if I have 1/4 the amplitude for this wave? How does that affect its energy? You need to be able to answer those types of proportional reasoning questions, so you need to understand the relationship. This symbol right here means is directly proportional to. I'm not giving you an equation that relates the two. I'm just simply telling you, hey, if you change the amplitude, it's going to change the energy and vice versa, and this is the relationship. Okay, so this would help you answer those types of questions, which you're about to see in just a minute. All right. These images were in the FET that you guys did the other day in the Google form. These waves have very different amplitudes. The one on the right, where these people are walking through, those waves come up probably to his knee, maybe a little under. This wave on the left is taller than this girl. And you can see that when the wave has a greater amplitude, a greater height to it, it has a lot more energy. It knocks her over. These people don't seem bothered at all. She, on the other hand, could be very hurt. That'd be pretty dangerous if she hits her head on something especially. But that energy is proportional to amplitude squared. So as that amplitude increases, it's not just a linear relationship. It's not, hey, I have twice the amplitude, there's twice the energy. Rather, it's squared. There's a lot more energy that is going to be transferred to her due to this change in amplitude because of that squared relationship. So amplitude is easy to see on a transverse wave, but it's difficult to see on a longitudinal wave because we can't really show it in a still picture that's printed on a sheet of paper. That's why I wanted to show you this in case you have a question about amplitude of a longitudinal wave. My transverse wave's easy, it's the one on the right. My amplitude is, again, my maximum displacement from equilibrium. So equilibrium is this blue dashed line in the middle, and you can see my maximum amplitude, positive amplitude up here at the top, and there is my arrow representing that distance, and then my minimum or my largest negative amplitude here at the bottom, And again, this is measuring that distance, but it's half the height of the vibrational path here. For a longitudinal wave, it's half the length of the vibrational path because my vibrational path is back and forth. And so if you focus on this red dot, I've labeled its vibrational path, and you can see half of that with equilibrium in the middle. You can see each of these two green arrows. So again, amplitude is a little bit trickier to see on a longitudinal wave, but it would look something like that image on the left. Okay, half the length of that vibrational path. All right, so I told you we would have questions with some proportional reasoning, so let's try this one. If you want to copy it down so you have an example, might be a good idea. It says an average ocean wave has an amplitude of 1.5 meters. A tsunami can be up to 8 times larger with amplitudes of 12 meters. How does the energy of a tsunami compare to the energy of an average wave? Again, I know that energy is directly proportional to amplitude squared. So 1.5 to 12, that is 8 times larger. It says it right here. So this is 8 times larger than this. Well, my energy is not going to be 8 times more. Rather, it's going to be 8 squared times more, or 64 times more, which is why tsunamis can cause so much destruction. Because when they are 8 times larger, they are going to be carrying 64 times the amount of energy, and that's more energy to do work on things like buildings and cars and knock you over, move things around, because they are able to apply more force, because they can do more work, because they have more energy. Okay, so again, this relationship, you're going to see questions where you have to use it, so make sure that you have it in your notes, and this is a good example if you want to write one down. These are your wave equations. We've already discussed these, but you may want to jot them down in your notes. Velocity of a wave can be calculated by multiplying the wave's frequency times its wavelength. Okay, because frequency is 1 over period, which is the next equation, you could also write this velocity equation as velocity equals wavelength over period, which would be distance over time. It would be the same thing, because if you put 1 over t right here, you have 1 times wavelength over t. Okay, so you could also write it that way, but you could leave them like this if you prefer. But frequency is 1 over period. Alternatively, period is 1 over frequency. They are inverses of one another. And then the last one, energy is proportional to amplitude squared. This is only going to be true for mechanical waves. When we get to our next unit with electromagnetic waves, that is no longer going to be the case. That's part of what makes things a little bit interesting in the next unit. All right, let's try an example calculation. Again, this would be something you could write down in your notes if you want to have an example to look back at. This is slide 33. It says, Brian and Tarek stand 8 meters apart and demonstrate the motion of a transverse wave on a rope. The wave can be described as having a vertical distance of 32 centimeters from a trough to a crest. I went ahead and labeled that in my picture. There's my 32 centimeters. A frequency of 2.4 hertz and a horizontal distance of 48 centimeters from a crest to the nearest trough. So let's label that too. Horizontally from crest to trough, 48 centimeters. Determine the amplitude, period, wavelength, and speed of such a wave. Okay, so let's do that. Amplitude, period, wavelength, and speed. Okay, now amplitude does have to do with the height of the wave, but specifically it's the amount of displacement from equilibrium. So it's not the total height, it's half the height, because it's how far it is from the middle. Okay, and so my amplitude isn't going to be 32 centimeters, but rather 32 divided by 2, which is 16 centimeters, or 0.16 meters. My period. They told me in the question the frequency of this wave, so I can find my period from that, because period is 1 over frequency. So 1 divided by 2.4 gives me a period of 0.416666, repeating. Okay, and so I have 0.416 repeating seconds. My wavelength. Again, wavelength is the length of the wave. You can measure it from crest to crest, or trough to trough, or equilibrium through one cycle back to equilibrium again. But I already have part of the length labeled, 48 centimeters. That is not the total length. That is only half of the wave, because the whole wave would be from this to the next crest. Okay, so 48 times 2, which is 96 centimeters, or 0.96 meters. And then lastly, we have the speed of our wave. And again, speed is wavelength times frequency. So I can take that 96 centimeters or 0.96 meters and multiply it by 2.4 to get a speed of 2.304 meters per second. For the record, I could have also done 0.96 divided by my period, and it would get the exact same answer. Okay, so again, be able to do these kind of simple calculations for a wave. And if you don't think they're simple, go back and look at this slide again. I'm on slide 34. And look at it again so that you feel more comfortable with these types of calculations, because you have some to do in your assignment today. For the rest of the period, you can work on the assignment 1302.1 waves problem set. It is due by 11:59 p.m. tonight, and you guys have 10 minutes left in class. So use that time wisely. Ask questions if you have them. Work with your neighbor, but figure it out. And if you can't figure it out in class, you're going to have to work on it at home.